In this example, we will anti-differentiate 1 divided by the square root of 4x squared minus 4x minus 3. Now, the first observation I have looking at this is it's a quadratic function in a square root. And I'm not seeing any obvious method to approach here in terms of an obvious substitution, an obvious algebraic manipulation. It's not quite in any of our standard forms, but completing the square for the quadratic will allow us to hopefully use a trigonometric substitution. So let's go ahead and do the algebra work to complete the square. So we have the quantity 4x squared minus 4x minus 3. In order to complete the square, what I would like to do is factor out the 4, so I simply have an x to work with. And I'm going to go ahead and leave the minus 3 out of there. And ideally what I would be able to do is rewrite as x minus some quantity squared. And in order to determine what quantity will be squared, we look at the coefficient of x and we divide it by 2. So the coefficient of x is minus 1, so we should be subtracting away 1/2. And note when we expand that out, we'll have x squared minus x plus 1/4. So in order for these two things to actually be equal to each other, I need to add 1/4, and now x squared minus x plus 1/4 is exactly x minus 1/2 squared, but I also need to subtract away 1/4, so that I'm essentially just adding 0. So we have minus 1/4 minus 3. So now if I distribute the 4 through, I have 4 times x minus 1/2 quantity squared minus 1 minus 3. So this is 4 times the quantity x minus 1/2 squared minus 4. So let's go ahead and put this to work. So having rewritten what's inside the square root, we now see that we are in a perfect position to apply a trigonometric substitution. So looking at our table of trigonometric substitution, whatever quantity here is being squared is what we would like to be equal to secant of theta. So we want to let, in this case, x minus 1/2 be equal to secant of theta. So x is 1/2 secant theta, and dx is going to, 1/2 plus secant theta, and dx is going to be equal to secant theta tangent theta d theta. And now, rewriting our integrand solely in terms of thetas, this becomes 1 over the square root, and the bottom will have 4 secant squared theta minus 4, and dx is secant theta tangent theta d theta. And once we've made this trigonometric substitution, remember our next step is to immediately apply that corresponding identity. And here the corresponding identity to apply is to remember that secant squared theta minus 1 is tangent squared. So what we have underneath this square root will really be 4 tangent squared of theta. So we have the secant theta tangent theta in the numerator, and in the denominator we have the square root of 4 tangent squared. So that would be 2 tangent d theta. So our tangent theta terms cancel. We have a 1/2 that pulls out front, and what remains is the antiderivative of secant. This should be, at this point, a common antiderivative that we easily can write down. So that would be the natural log of the absolute value of secant theta plus tangent theta. And our last step, as with any trigonometric substitution, is to rewrite back in terms of this original variable x. So in order to do so, we draw the right triangle corresponding to our trigonometric substitution. So our trigonometric substitution is x minus 1/2 is equal to secant theta. Maybe a slightly more convenient way to write that is in terms of cosine. So cosine is 1 over secant, so this will be equal to 1 over x minus 1/2. So cosine of theta is 1 over x minus 1/2. And if we use the Pythagorean theorem to label this remaining side, that will be x minus 1/2 quantity squared minus 1. And now, rewriting in terms of x's, well, secant of theta we know is x minus 1/2. And tangent of theta, looking at our triangle here, opposite over adjacent, gives us the square root of x minus 1/2 quantity squared minus 1, all plus c.